Yeah, so this is propagating tree. Uh, the basic problem that you should have read by now. If you haven't, then that's an issue on your side. So basically, you have a tree. You have nodes. What the fuck? Why do we? Okay, let's example. Let's pick up some example. Yeah. Open up. What the fuck? Okay, you have a tree. Your tree has the node will always be, the root will be always the node 1, and all nodes have some values. So like this, so this node has some value, but its number is 1. So cool. So there are two operations that you can process here. Operation 1, that basically changes the value of node X and adds VAL to its original value, as well as for all the children of this node, minus VAL are added. So basically val is subtracted, and then the similar operation is done for all the children of those children until a leaf is reached. And the second operation is to find what is the current value of the node X. So let's copy this and let's open this, and let's see if we can paste or not. Okay, this is pretty. So let's create this tree. So we have a node 1, that is the root. 1 is connected to 2, 1 is connected to 3, 2 is connected to 4, 2 is connected to 5, and the values are, 1 has the value 1, 2 has the value 2, 1, 1, 2, as I have taken from here. So this is our tree. So let's say these are the operations. So first operation is of type 1, and the second node is to be added by 3. So second node is this, you plus 3 here. Then for the children you do minus 3, and there are no children of these children, so you don't move forward. So this will be 5, this will be minus 2, this will be minus 1. Again for this operation, this operation, you add 2 to 1. So you have this guy, you have to add 2 to this guy, and for the children you do minus 2, and for their children you do plus 2. So it's more like a level wise operation, as you might have noticed. But the issue being that, let's say you have a tree, and this is a funny tree, but it doesn't laugh. Sad tree. Yeah, so let's say this is the guy where you make change, the original change. So change can only be percolated down for this tree only. So this level gets a single change, this level gets a single change, but not whole of the level, only a part of it, right? So so if we could represent this tree in arrays, let's say we have some method, this is our magic funnel mf, or yeah, so let's say this is our magic funnel and a tree goes in, and an array representation comes out. So, and the array representation is such that you can actually do these operations. So let's say I can do a subtree is to be represented as a sub array of the array. Okay, so let's big rub, fuck off that tree, nobody likes you. Okay, so this actually can be done. There's a concept of visiting trees nodes. Okay, so let me go and actually open this one's tutorial, because I'm a little bitch and I will cheat my way to the top. Okay, what the fuck? Why is everything in Russian? Who is this? Dev1 C. This is not, I think Dev2 E should be, yeah. So this is our answer. So this is the part. If node subtree is contiguous sequence, yes, exactly, that is what I'm saying. This guy copied from me. Yes, I forgot the name of the topic. It is discovery time and finish time. So what do you, so there's this concept of discovery time and finish time that is pretty fucking easy to understand. So I will actually show how it is done. So let's make 3 arrays: discovery array, start array, and finish array. So as the name suggests, discovery array stores the nodes in the order they are discovered in the DFS. Start array stores the starting point at which a particular node was discovered, and the finish array stores the last time point that came into the subtree of that node. That's not a good explanation. Let me think a better one. Let's say okay, I think I should give an example so that will clear it up. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you get it. So basically what you can do is start a timer at 1 because I like 1. So you have t is equal to 1 at this point. So you are visiting 1. So you add that to the discovery. So the first node is the node that was discovered. And since you are visiting it right now, this is the start point of the visiting. So yeah, actually during the DFS what you do is this is DFS. So you go to the node. This is the first point of the visit. Now you visit all the children and children's children and blah blah blah, whatever the fuck, and now you go back, right? So this is the second visit after every child node has been visited. So the point at which this first visit is done, we are saving that in start, and the time at which the second visit is done, we are saving that in finish. So what's the time? 1 for the node 1. Give a fuck? No. So you go to 2 second because second is discovered after 1. What's the time? You increase time by 1. So starting point of 2 is 2. We do not actually finish right now. We'll fill it up when all the children of these nodes are visited. So let's remove this part. The tree is too big. It will take too much time. I do not have time. I have to sleep. For that. Yeah. Okay. So now you go to 4. Okay. And for 4 time is 3. Right. So you have actually a gap here for 3, and for 4 you say 3. 4 gets over. Time is again 3. So 1, 2, 3, 4. So 4 got the first visit at 3, didn't visit any of the children, and finished at 3. Went back to 2. 2 does not. 2 has not completed its visit, so now it goes back to 5. And the visit increases whenever you go back to your children, but does not increase whenever you go back up. I saw an example, but fuck that shit. I'll do it this way only. So this increases. Time is 4. Node is 5. So this is 4. This is 4. And you go back. 2 is completed. 2 is completed, and the time is 4. Now 1. Go back to 1. No children. Go back to 3. 3 is visited for 5. Now 6 is visited for 6. 6 gets ended at 6. Go back to 3. 7 is visited for 7. Ends at 7. Go back to 3. 3 is ended at 7. 1 is ended at 7. 1, 2, 4, 5, 3, 6, 7. So you have these arrays. Now how does this help with array representation, you will ask. Let's say I want this part. I want to know what's the sub array for 3. I will say go to your start node, find the value for 3, go to your finish array, find the value for 3 from the index 5 to the index 7. That is your subtree. So this is some second year level shit. Which I should have known, but I'm dumb, and everything takes time because I'm slow. So yeah, this is the way. So you'll say let's just fuck everything up. Yeah, so okay, you'll say कि this works if whole subtree had to be plus world or minus world. Like instead of the operation that is alternating, we only have a single type of operation. That in that case this is useful, but how the fuck is this useful when I do this? No, tell me. So this actually is a good question, and it took me 7 years to understand how this can be done. So okay, this is your tree, and I hate this tree from the bottom of my heart. Your motherfucking code forces comes and says, hey bro, for this node I will do plus x. I'll say cool, and then I'll cry. No. So what's the point of this thing is कि you actually divide the tree into two parts. The odd levels and the even levels. So you have two types of levels here. Why do I do this? Simple. Not reason. No. Absolutely. Yes. So the point here is that let's say you have a change at this point. So this will be odd level change, even level change, right? So let's say we will go for even levels, we will take the value as it is, and for odd levels we will negate them. So basically what we are doing is we want to keep the root node as the reference for these levels. So let's say there's a change here and there's a change here. So if let's say there's a positive change here, a positive change here. So the issue here is that these changes are localized. you do not have a reference point. So this will be negated and this will be a positive, but if you see this one, then this will be positive and this will be negative. So these two will be different in this case. So what we are trying to do is actually map them to the reference level. Okay, so once we decide that we are doing this, we can actually come back and say that, hey, okay, for all the evil ones I will add, and for the odd ones I will negate. So if there's an addition, we will actually save it as a negative, so that when we are finalizing a thing, it will be a double negative and it will go as a positive. Okay, so this needs a good example. Let's say this is our tree. And these are evil. Nope. These are old levels. And these are evil levels. So what I do is I'll say, okay, whatever the input be, I will add the evil levels and I will negate the odd levels. I don't care whatever the value is maybe. So if you know that the negative ones are to be subtracted and the positive ones are to be added, so if there is a positive change at the odd level, you'll make it a negative change. So afterwards, when it is actually counted as a negative change, there is a double negative and it becomes a positive change. Similarly, if you know it is a negative change, you add it, and a minus of a positive one will become a negative change. So let's take an example here. Let's make another sheet just because I can. No paper is being wasted, so why not? Let's say everything has a value 0 and I'm doing a +2 here and a -3 here, then asking the value of this. So level wise, let's also write levels 0, 1, 2, 3. Mom, no, she's not that small. So okay, these are even and these are odd, which is different from what I told you, but okay. So what I said, key for the odd ones I will negate them, and for the even ones I will add them. So this is odd, so I will negate them. So this is a -2 change for whole of this part. So, and this is, so let's say this has been described as an subarray. Let's say this is A, B, C, D, E, F, G. Now whatever the order that may be, actually I will have to follow the fucking order. What will be the order? Discovery A, B, D, E, C, F, G. Okay, so I made a change in 2. Okay, that will change some things. I don't care. So okay, so for whole of this array I will say add 2 for everyone. Cool. Everyone was 0 initially. Now for C I subtracted 3 and it is an even level, so you will do what the number came. So for CFG you do -3, my lord. Okay, now we have to get the value of f, right? And f is at an odd level, so there is a negation that is needed to be done here. I will need to read my code because I think I forgot one part. Yeah. How is the query doing? Level of the node matters, and we are querying. So for whole of the sub array, we are getting the summation. Yeah. So let's sum these up. Minus. I have a fucking rubber. -5. -5. -2. -2. -2. Okay. So you know this is an odd one. So what you will do is double negation. Yeah. Okay. So double negation. You will negate this guy. So negation of -5 is equal to 5, right? So let's see what the correct value would be. So +2, in that case -2 here and +2 here, and for -3 there will be a -3 here and then +3 here. So when you add these two you will get a +5. Bonanza supreme, bro. So you'll ask me how to do these additions. You can do either use segment trees for this, or you can use bits or Fenwick trees. Fenwick trees actually are more simple to implement than segment trees, so use it. I think that is a pretty standard problem, so you can directly use that. Otherwise it's solved, I guess. There were two major things. First was the discovery and finish time, and the second one was this odd and even levels. Once these two are clear, you got it, bro. Woohoo, yeah. Bye.